Okay, let's get started. So I hope you all had a good weekend and enjoyed the snow. So last time we were talking about the real numbers and sets, and we didn't quite finish with sets. So I'll start today by just saying a few more things about them, and then we will move into talking about functions. So here's so one way that we saw last time of making sets, well, I guess two ways. One is you can just inside of curly braces list the elements. And then we also saw set building notation. So we had like ways of making sets. So we can just list the elements. And then we had the set builder notation where you specify sort of where your elements are coming from and then specify some condition. Something like that. So set builder notation. And right now I'll give you two more ways to make sets just by combining the sets that we have in different ways. So this is going to be union and intersection. So let's start with union. I'll make a definition. So let's let A and B be sets. And then the union is just going to be combining those two sets into one larger set. So the union of A and B. So this is going to be a new set, and the way that you write it is, so I'll just say that this is written as A, and then it's like a sort of like a U symbol in between them. So A union B is the following set. And I'll write it down for you using set builder notation, and then I'll sort of explain what it's saying. So this is, so A union B is equal to the set of x's such that x is an element of A or x is an element of B. Okay, so what this is doing on an intuitive level is just combining the two sets together. And I want to focus in on this word or for a second because in math it's used in a very specific way that is sort of in conflict with the way that we use it in the English language. So, in English, say you're at a restaurant and someone says, "Do you want soup or salad?" Um, that means you can have one or the other one, right? You cannot, like, they're not really asking you if you want both. But in math, it's allowed for the two sets to overlap, and we would still consider X to be an element of the union. So, or just means at least one of these conditions is satisfied. It could be one, it could be the other one, and it also could be both of them. So to draw this as a picture, there's how you can visualize it, is you might have your set A, which I'll just denote as this blob. So everything inside of that blob is an element of A. And then I might have another set B. So here's my other blob, and perhaps they overlap a little bit. So the elements of A union B, I'm going to use like a pink highlighter for this. So that would be just anything that's in B, also anything that's in the overlap, and everything that's in A. Okay, so every member of either of these three regions satisfies this condition of being in A or being in B. Okay, are there questions? So let's do an example with intervals. So let's think about the interval 0, 1, and let's union that with the interval 1/2, the closed interval 1/2 to 5. Okay, so how might we go about figuring out what this union is? So the way that I like to do it is actually just to draw a picture of the real number line. So maybe I'll draw this interval in red and this interval in green. So here's my real number line. And I'll just write down where all of these numbers are. So we might have 0 there, 1, 1/2, and then somewhere out here we have 5. So it's not really to scale, but just getting them in the right order is all that's really important. So I have the interval from 0 to 1. So that's going to look like this. I have an open dot there and an open dot there. And that's my interval from 0 to 1. And then I have the closed interval from 1/2 to 5. So it looks something like that. So then the union is just going to be combining these two intervals. So that's going to be in total, right, the open interval from 0 to 5, and that's going to be closed on that side. So this is the interval from 0 to 5. Okay, does that make sense? Other questions? I think that just drawing a quick little sketch is probably the easiest way to approach problems like this. Okay, so then the other way to combine sets is what it's going to do is it's going to capture this intersection. So this is called the intersection of the two sets. So I'll make a definition. So again, we'll let A and B be sets. Then the intersection of A and B, which is written. So basically you just take that union symbol from before and flip it upside down. So it'll look like that. So it's A intersect B is the following. So this will be A intersect B is the set of elements X such that X is an element of A and X is an element of B. Okay, so in order to be an element of A intersect B, X has to satisfy both being in A and it has to satisfy being in B. So that's our condition for being an element of this set. So I'll draw the picture like before. So if this is A and this is B, then this little section in the overlap would be the intersection. So intuitively, this is elements that are in both sets. So elements that are in A and are in B. Okay, is it making sense? Good. Okay, so let's do an example again with the intervals. And maybe we'll just go back to this same picture. So if I wanted to look at the interval from 0 to 1 intersected with 1/2 to 5, then you can just draw the same picture. And now you're looking for where the two sets overlap, right? So it would just be this little bit in the middle. And so that is the closed So it'll be closed on the left-hand side. It includes 1/2, and then it goes up to 1, and it doesn't include 1. Okay, does that make sense? Does it make sense like how to figure out what the endpoints are and whether or not they're open and closed and all of that? Okay, sounds good. So, okay, that was everything about sets. So we'll move into talking about functions. So functions are really the main object of study of calculus. And for the most part, we're going to be looking at functions whose inputs are real numbers and the outputs are also real numbers. So let's spend a little bit of time just getting used to them and getting some familiarity with what they are. So I'll just give you a definition of what a function is. So for this conversation, I'm gonna say what a function from any set to any other set is, but 95% of the examples that we do in this class will just be from the real numbers to the real numbers. So I'm gonna let A and B be sets again. Then a function from the set A to the set B. So this is going to be a rule where I'm allowed to input any element of A and it will spit out some element of B. So this is a rule which assigns to each and every element, let's say X in A, an element of the set B, which is usually called f of X. So a function from A to B takes inputs in A and spits out an output in B. And I want to emphasize that, so I'll just write this. Oops, I didn't put a T here. So every input, so every element of A has an output, and it only has one output. So each input has one output. And sort of a shorthand way to write that f is a function from A to B is to write it like this. So you put the symbol that is the name of your function and then a colon, and then you write A arrow B. So this just reads as f is a function from A to B. So for us, almost always A and B will be the real numbers or a subset of the real numbers. Okay, maybe I'll pause for questions. It seems like we're so far so good. So three other pieces of like terminology. So the set A is called the domain. And the set B is called the codomain. And then there's one other sort of set that we care about, and that is the set of outputs of F. So that's a little bit different from just the codomain, because this could be, so basically the idea is the codomain is just like any target set, like we're just gonna spit out numbers and I just want to write down a set where those numbers live. The other set that we're going to talk about is the range, which is the set of actual outputs of F, which is always going to be a subset of the codomain. So the range is the set of outputs. So this will be the elements, I'll say Y in B, such that Y is equal to F of X for some X in A. Okay, so as I range over A, maybe I shouldn't say the word range because we're using it in the definition. So as I pick out elements of A and see what F does with them, I'm populating the range with all of its elements, right? So if I stick all of the elements of A into F and look at what elements of B are spit out, that is the we'll do an example in a second. So you can just remember the range is always a subset of the codomain. Yeah. Okay, maybe I'll do the example and then we'll see if there's questions. So let's define a function f from the real numbers to the real numbers. And let's say that this is given by the equation. So if I input any x from the real numbers, then f is going to spit out x squared. Okay, so what does this mean? This means for any x in the real numbers, the function f is assigning x squared to x. So it just takes the input and squares it. So let's look at some examples. So f of 0. So we're just going to take that input and square it. So 0 squared is 0. So f of 0 is 0. F of 1. So 1 squared is 1. So we just get 1 again. F of 2 is 4, and so on. You can keep calculating. And one thing that I want to point out is that if I plug in, so say I put in -1, I also get 1. So here, I have 2 inputs that give me the same output, and that's okay. So 2 inputs with same output this is okay. But notice that given any input, there's only one output, right? The function is just like a machine. I feed it something and it just squares it and spits that out. It's not like non-deterministic in some way where I am possibly going to get more than one answer. It's like one input, one output. Okay, so what is the range of this function? So the range of f. So we know the domain is the real numbers, the codomain is the real numbers, and that's just given to me by this notation, right? So this is just telling me this is going to be the domain and this is the codomain. But what is the range? Yeah.
0 to infinity.
Yeah, so this is going to be the interval, so closed at 0, because we already saw we have an example of something that is sent to 0, to infinity. Yeah. So that's the set of possible outputs of f. And yeah, so like why this difference between range and codomain? Like why is this meaningful? So when you're writing down the function, it might be, depending upon what the function is, it might actually be tricky to figure out what the range is, right? So we can just do the easy thing and just write some set that for sure is going to capture all of the outputs, and then later on worry about what the what the actual set of outputs is. Does that make sense? So it may just be like too difficult to figure out precisely what the range is. So like we could have written, so this is like an aside, we could have had f go from the real numbers to this interval. Oh. But you may not want to do the work of figuring out what the range is always. So it's just easier to write R here instead. Okay. Are there questions? Okay, so let's talk about how to visualize functions. So this is called the graph. So first of all, let's just consider the following set. This is going to be the set of pairs x comma y such that x and y are elements of the reals. Okay, so first of all, I just want to remark that I've sort of broken the rules of the set builder notation here, right? And why am I saying that this is like rule breaking is because on the left-hand side, I didn't really specify, I'm taking elements from a specific set and I'm specifying a condition. I sort of switched it around, right? So this is like, you can almost think of this as like a parametric way to write down sets. So what do I mean by that is that on the right-hand side, I'm specifying some parameters and like where they live. So I'm going to say like x and y range over the real numbers, and then I'm going to take those real numbers and create this other thing with them. And so you can think of like those x and y are like tracing out the elements of this set, which are ordered pairs x comma y. So is this making sense? So this is like another way to make sets. Just to make this a little bit clearer, let me go back to our definition of the range. So this same set I could write, for example, as the set of f of x's such that x is an element of the reals. Right, so x varies inside of the real numbers, and then we're collecting up all of the f of x's and putting those in a set. Does that make sense? So this is like another example of that same technique for set building. Okay, are there questions? You guys look a little bit puzzled. That's why I'm pausing here. It seems like you've reacted, to this information differently than you normally do. So I'm just seeing if anyone has a question. Okay. Okay, so let's think about this set. So we're taking the set of ordered pairs of two real numbers. So I can draw this in the following way. So let's draw a picture. And by the way, this is called, we usually write this as R squared because it's like taking two real numbers. Okay, so how do we draw this as a picture? So what I'm gonna do is, so let's forget about y for a second. So I know how to draw a picture of just one real number, right? Just an x. So we have the real number line. So this is like the set of x's. And then I also have, if I ignore the x, I also have a choice of y value, right? So that gives me another real number line. So here's like my choices of y's. And then the convention is to just say that these two lines intersect at 0, 0. This is really just a choice. But that's usually what we do. And then if I take, let's say, any point out in here, this is like some point A comma B, where if I drop a perpendicular line here, this intersects this real number line corresponding to the x values somewhere, and that's going to be at the location A along that real number line. And then I can also go out this way and see where I hit the y, it's called the y-axis, but where I hit along that that real number line corresponding to the choices of y's, and that gives me some number b. Okay, so this thing is called the Cartesian plane, or the Cartesian coordinate plane. And this is going to be sort of the ambient space where we can picture functions. And the reason why we picture functions in there is because a function will take in one real number and output another real number. So it's sort of a natural space to just keep track of pairs of real numbers, right? So here's what the graph will be. So let's make it a definition. Okay, so let's take a function, and it will be a function from the real numbers to the real numbers. So f is going to go from R to R. So the domain is R and the codomain is R. Then the graph of the function f is, so it's going to be a subset of R squared, or R2, this Cartesian plane. So it's a subset of R2 of points of the form x comma f of x, where x is an element of the real numbers. Okay, so let's I'll write this down as a set. So this will be the set of points x comma y in R2 such that y is equal to the output of f when I put in x. Okay, is it making sense? So here's another way to write this, is I could also write that this is the pairs x comma f of x such that x is a real number. That's sort of in the second way of building sets, how you could write that. So these are equivalent. Okay, so let's do our example. Same one as before, just f of x is equal to x squared. Okay, so we're going to start with R2, this Cartesian coordinate plane. And then inside of here, I want to identify the pairs of points where the x-coordinate is anything, it's any real number, and then the y-coordinate is exactly the output of f. So, for example, we knew that f of 0 was 0. So that means that 0, 0 is a point in the graph of f. And then another one, we know that f of 1 is 1. So let me label 1, 1. And we also had -1. And we had that point as well. And we'll do one more. So if we have 2, we know that that outputs 4. This is 2, 4. Okay, so these pink points are points that we calculated that we know are on the graph of f. And you've probably seen this picture before, so you know that in the end, if you start drawing all of the points that are in here, you'll get this parabola. Okay, are there questions? So a graph is like a pictorial description of a function. It's like a way that you can visualize what the function is doing. Okay, so now what we're gonna do is, so we sort of have an idea of, if I hand you a function, how might you draw the graph of it? And I guess we're going to go into a lot more detail about that because it can get very, specific depending upon the features of the particular function that you have. But like one strategy that you could take is to just start plugging in lots and lots of real numbers and see what the output is. And then you can just draw all those points on the graph. So what we're going to talk about now is how to go the other way. So if I hand you a graph, how do you know what function I'm talking about? So this is what we'll look at. So how to take a graph and figure out the function. And I'm going to start with a picture, so we have an example to work alongside. So let's say, so this is my Cartesian coordinate plane, here's the x's and here's the y's. And I'm just going to draw some random like squiggly thing. Okay, so let's say this is my function, or my graph. This is the graph of some function. And I want to know, let's say for a particular element a in the real numbers. So let's just put something here. How do I figure out what f of a is? So the task is, given a real number a, what is f of a? So here's how you would figure that out from the graph. And the book calls this the lift and project method, which I think is just a handy way of remembering sort of what the strategy is. So this is the lift and project method. Okay, so step 1 is lift. So what I'm going to do is draw a vertical line segment from the point a comma 0 and see where that intersects the graph. Okay, so draw vertical line segment from the point A0 in our Cartesian coordinate plane and see where it hits the graph. Okay, so maybe I'll draw my lift in green in the picture. So I'll start at A0. So yeah, this is A comma 0. And I'm just going to start drawing a vertical line, and then it intersects the graph somewhere. And then step 2 is the project. So then what you're going to do is you're going to draw a horizontal line segment from this point where you hit the graph, and we're going to go towards the y-axis. So draw horizontal line segment from the point found in step 1 to the y-axis. Okay, so okay, so I'll do this in red. So now I'm just going to start going to the y-axis, and I hit that here. Okay, and then this point on the y-axis, so its x-coordinate is 0, and its y-coordinate is going to be exactly f of a. Okay, so why is that? So we started with our point A, and we saw where does the graph, where is the graph when we're at x equals a? So that's this point. And by definition, since that point is on the graph of f, this point is a comma f of a. And so then the project step just tells us what was that second coordinate f of a. Okay, are there questions? So far, so good. Okay, well, one thing you might wonder is, I just drew this pink squiggly line, but how did I know that that actually was the graph of some function? So if I just draw some picture inside of R2, how do you know whether or not that is the graph of a function? And so here's how you can determine that. So how do you know if a subset of R2 is a graph of a function from R to R? So all we really know about functions is that they have to take any input from their domain and output one value in the codomain. And so that's really the only restriction that we have on what a graph can look like. So we know that every input has one output. So how do we transform this into sort of a rule for deciding whether or not a subset of R2 is actually the graph of a function? So here's how this works. It's called the vertical line test. And this just says that if I take a vertical line and sweep it across R2, then it has to intersect the graph of the function once everywhere, right? So let me just write this down. So a vertical line in R2 must intersect the graph exactly once. So why is that? If a vertical line intersects the graph more than once, then that means I'm not a function, right? Because that input had two outputs or more outputs. So that's not a function. And furthermore, if I don't intersect the graph anywhere, then that is an example of an input that has no output, which also isn't allowed. So let's look at some examples. So let's say this pink thing is supposed to be, is the thing that I'm wondering whether or not it's a graph. Well, there's multiple problems with this because let's say I put a vertical line here. I've intersected the pink shape twice, right? And that's bad because that would correspond to a function where whatever this x value is, that input had more than one output. And also over here, I don't intersect at all, which means that this input has no output. So this one is not a function. On the other hand, let me draw another example. So I'm gonna have some wacky thing. Say it jumps here. So this one is okay because if I take any vertical line and I start dragging it across here, it's always intersecting exactly once, even at this weird spot where it jumps, right? We still have that input has one output. We keep going and we have just one intersection point everywhere. Okay, is this making sense? Yeah. So yes, okay, this is a little bit of a technical point. So let's say we had something like this, right? So you've seen graphs like this before, right? Where the function is maybe not defined at x equals 0. So let's say, so this is like 1 over x, right? So 1 over x this is like the loophole. 1 over x is not a function from R to R. It's a function from R minus 0 to R. So, okay, so yeah, so we need to amend the rule for this. So this is a function. So basically we're just gonna, since when I can't divide by 0, right? So this function has no output if I input 0. So I'll just restrict the domain. So this is a function from R, and the way that you write this is backslash, and then I'll specify the set that I want to remove. So I'm just gonna list the elements that I can't plug into this function. So R minus 0 is like how you might say this. This is a function from R minus 0 to R. Okay, so how would we fix our vertical line test? Well, I don't care if the vertical line test fails at x equals 0 because that's not a part of my domain anymore. So like if we wanted to rewrite this, so a vertical line in R2 must intersect the graph. So a vertical line at a point in the domain of the function. So another way, so we were going from R to R, but if you replace this with something else, then you would just worry about points that are in your domain. Yeah.
Second strike against that graph being that is the vertical line.
Yeah.
So I guess I'm wondering how that squares. It's not.
Yeah. Yes. Yeah, exactly. So like, let's say we have this picture. And I'll label, let's say this is -1 and this is 1. Okay, so I'll just take like the upper half of that picture from before. So something like that. This is not a function from R to R, but it is a function from -1 to 1. So okay, does that make sense? Okay, good. So I think, okay, so let's sort of the last thing about functions is I just wanted to recap some common types of functions that you'll encounter in this class and you've probably seen before. So this is just some key types of functions. So the first one is just constant functions. So that means that given any input x, the output is just some fixed number c. So where c is just some fixed real number. So no matter what input you give it, the output is always that constant. So for example, you might have f of x equal to 3. And what does the graph of such a thing look like? It would just be a horizontal line at y equals 3. Okay, other types of functions. We have linear functions. So this is something like f of x equals mx plus b, where m and b are real numbers. And the number m is your slope. So this is a measurement of how steep the line is, and b is called the y-intercept. And the graph of this will just be some kind of line. So the numbers m and b will sort of control like how steep your line is and where it is located, but it always looks something like that, or it could be going down the other way. Okay, then we also have polynomials. And with this, maybe it's easier to just write down an example to start with. So this will be like 17x to the 5th minus 2x to the 4th plus 4 fifths x squared plus 7. So basically, what is this? It's any function that's obtained by adding or subtracting terms which come from multiplying a real number by some power of x. So this is a sum of terms where each term is a real number times a non-negative integer power of x. Okay, and we'll talk a lot more this semester about how to draw the graphs of polynomials, but I'll stop there for now and I'll see you all on Wednesday.